How can biomechanics contribute to the current massive digital health movement? I'm going to share a study that takes a step towards this. Our team developed a mobile and self-guided biomechanical assessment and deployed it in a nationwide study accessible to anyone with a smartphone. My name is Melissa Boswell, and I'm a postdoctoral scholar in bioengineering at Stanford University. And I'm honored to be presenting in the Young Researcher Award session today. Many of us entered the field of biomechanics to help people move better and safer. And we know from decades of research that assessing one's biomechanics can help us identify, understand, and design treatments for diseases and disorders that affect movement. One movement that is particularly indicative of one's physical health status is the sit-to-stand transition. Sit-to-stand transition tests are widely used in clinics to test physical function by measuring the time to complete the test with a stopwatch. However, movement is a key determinant of sit-to-stand strategies. In fact, kinematics of the sit-to-stand test, like joint angle ranges and velocities, are related to a number of health factors, including frailty, age, and osteoarthritis. So while timing of a sit-to-stand transition is indicative of physical function, this can be influenced by a wide range of diseases, injuries, or demographics like age. Kinematics, on the other hand, can give additional insights that are more sensitive and specific to certain conditions. However, biomechanical assessments have traditionally been limited to laboratories equipped with expensive and technical equipment that aren't easily scalable or accessible in a clinic or at-home setting. This is one of the largest challenges in the field, hindering the impact of biomechanics research. But it leaves the opportunity to develop digital tools that enable biomechanical assessments at a large scale. In recent years, there has been tremendous growth in tools that enable biomechanical measurement outside of the lab. Things like inertial measurement units, wireless EMG sensors, shoes instrumented with pressure sensors, and pose estimation algorithms that can predict the location of joints from 2D video. Motion analysis from 2D video is a particularly exciting opportunity, as 83% of the global population owns a smartphone and could access their own pocket-sized tool for quantitatively self-assessing movement. These algorithms, such as OpenPose, shown here, can detect poses from videos outside of the lab. But are they accurate enough for medical applications? In our study, we test if pose estimation algorithms are robust enough to enable real-world measurements that give people insights to estimate important health-related measures. The goals of our study were to develop an online tool to capture and automatically analyze self-collected smartphone videos of the 5-repetition sit-to-stand test and deploy it in a nationwide study. To validate the tool by testing for previously determined relationships between sit-to-stand parameters and demographic and health measures, and leverage our large data set to explore new relationships. We chose to focus on the most common variation of the sit-to-stand test, the 5-repetition sit-to-stand test, where an individual goes from sitting to standing 5 times as fast as possible with their arms crossed in front of them. Here's an overview of the study. Participants collected a video of their sit-to-stand test at home using a smartphone. The video was then uploaded to the cloud, and the computer vision algorithm OpenPose detected joint locations throughout the movement. Our machine learning tools computed the key transitions of when the participant rises from the chair and returns to sitting. In addition to time to complete the task, we also compute other key biomechanical parameters like trunk flexion. So from the user side, this looked like going to our website, sit2stand.ai, to join the study, completing a series of questionnaires to make sure they qualified and the study was safe for them, and after qualifying, they also signed the consent form digitally. They got a video and written description of the test instructions, and the option to either record or upload the test. During the recording, they were instructed to have another person record them 5 to 10 feet away at a 45-degree angle. The video played back for their approval before submission, and then they were immediately directed to a health survey. And at the end of the survey, they were given their video with the pose estimation results overlaid, which many participants shared that they really enjoyed. We had close to 500 individuals complete the study entirely self-guided across 35 US states. This is over 35 times the median number of subjects in traditional biomechanics studies in just a few months with minimal researcher time and resources required. Because of the accessibility of the study, we were able to collect a diverse sample. In the 405 participants that were used in the final analysis, the age of participants ranged from 18, which was the minimum age to participate, all the way to 96 years of age. We had a range of BMIs from underweight to obese, and a range of different ethnicities and races. We also had about an even distribution of sexes. Here are the many different videos we collected from across the country. It was amazing to see so many people able to participate from their living rooms, their kitchens, and even outside. From these videos, we get a glimpse of the many different ways people perform the test, and I'll zoom in on a few examples of these different movement strategies. So here is a video of a participant who you can see can pretty easily go from sitting to standing with control. In the second video here, you see an individual who tends to lean further forward in standing up, using their momentum to help them rise. And this person also has knee osteoarthritis, which I'll discuss in the results. This individual here is optimizing for speed, also leaning further forward, but not necessarily to use it as a way to increase their momentum, but to optimize for speed. And then this participant here, you can see, takes on a combination of these different movement strategies. So first, we compared the results of our study to the results of past in-lab studies. Similarly, we found longer times to complete the 5 repetition sit-to-stand test were associated with an older age, shown in the plot here, a higher BMI, and a lower physical health. Larger maximum trunk flexion when going from sitting to standing was associated with a diagnosis of knee or hip osteoarthritis, even when controlling for age, sex, BMI, and time. It was also associated with increased age. The relationship between trunk flexion and osteoarthritis indicates that the kinematics we obtain from video may give additional information about health and functioning or particular diseases than timing alone. A larger trunk flexion among those with osteoarthritis also makes sense from a biomechanical perspective. Compared to a normal sit to stand, with a larger trunk lean, which is shown on the right, the knee joint is closer to the ground reaction force and the knee joint moment is reduced. With a linked segment model, such as the one shown here, studies have found that a 20-degree increase in trunk flexion reduces the knee joint moment by about 30%. Similarly, in a musculoskeletal model, weakening the knee extensor muscles, which we often see in individuals with knee osteoarthritis, leads to increased trunk flexion as a compensatory movement. Our large and diverse participant pool enabled exploratory investigation in different study population subgroups. In one such analysis, we found trunk flexion angles differed across racial and ethnic groups. Because 2 of these groups were non-parametric, shown here are the results from a Kruskal-Wallis test and a post-hoc Duns test. There have been very few studies examining differences in biomechanics across races, but in a recent study, Dr. Charisse Hill and colleagues found racial differences in gait mechanics. They concluded that equivalency in gait measures between racial groups should not be assumed. Our finding is hypothesis generating, and more studies need to be carried out to better understand these differences. But similar to the conclusions of Hill, we cannot assume similarity between different racial groups, and future studies need to make racially diverse study samples a priority. In individuals 50 years of age and older, greater trunk acceleration was associated with higher mental health. Perhaps these results indicate that people with higher mental health are more willing to stand up quicker or are less stiff in their upper body movement, leading to higher trunk acceleration. But this is entirely speculation, and similar to our analyses comparing kinematics to ethnicity, these findings are exploratory and hypothesis generating. But it is exciting to see that there may be relationships between mental health and the way we move. While it was exciting to see all the places and ways people performed the test, this inconsistency was also perhaps the most significant limitation of the study. Not all participants kept their arms crossed in front of them or appeared to do the test as fast as possible. All the chairs were of different heights and cushioning. Camera recording angle, height, and distance also varied. But in our study, we asked for participant feedback about their experience, and I think that this, in combination with input from experts in user experience and design, will be really helpful for making digital tests more consistent and usable in the future. We also wanted to share that with the publication of this work, we will be releasing tools, datasets, and code all freely available. So a simplified webpage is accessible to researchers to plug into their studies. An open source de-identified dataset of close to 500 participants performing the sit-to-stand test with matching survey measures, including measures not included in the analyses shown today, will be available, as well as all code for the website processing and analysis that will be freely available on GitHub once along with the publication of this manuscript. So in summary, we ran a large nationwide biomechanical evaluation of lay people at home using commodity cameras through our web app, which collects and automatically analyzed videos of the sit-to-stand test. These at-home recordings contain signals predictive of the presence of osteoarthritis and other health measures. Overall, the study shows that digital biomechanical analyses are possible and have the potential to become a supplementary endpoint for clinical trials as an at-home health monitoring tool. My vision is that we can deploy similar at-home tools to quantify biomechanics as a marker of health over one's lifetime. And with these tools, we may, for example, be able to detect ACL injury risk, recommend specific strengthening programs, detect osteoarthritis and then prescribe personalized gait modifications, and warn individuals at risk for falling. And in this way, we can apply biomechanics in the real world to help people move better and safer, and leverage biomechanical measures as a new biomarker of health. I want to thank all of my co-authors, especially Łukasz Kaczynski, as the study would not have been possible without him, as well as my lab for their support, and our participants for making this work possible. Thank you to my funding sources, and thank you to the World Congress of Biomechanics for the opportunity to share my work and learn from all the other incredible researchers at the Congress this week.